now let's start with the idea of normalizing flow. And the normalizing flow idea is eventually coming from this latent space perspective. So what we can always think, as I told you, we can think of the data, whatever it is coming from one latent space, right? Now, the point is that if we can target one latent space, which is easy to sample, and we can learn how we can get from that latent space into the data space, then the problem is quite easy, right? Because I am going to sample that latent space easily, like is, for example, a Gaussian latent. So I'm going to sample that Gaussian random variable easily, and then I pass it through that transform, I'm going to get my data, right? So this is the idea of flow-based models. That's all of it, right? And now we're going to start with the flow-based models. I mean, eventually, many of those implicit approaches, like GAN, are again thinking of the data generation in the same form. So, but let's start with the most basic one, which is the normalizing flow. And before we start, let's just consider one simple probability exercise that we get the idea how all the derivations are done. So say I do have one random variable z. And you really right now don't need to think about a vector. Just think of z to be one random scalar. And one thing that you should keep in mind is that we assume z is a continuous random variable, right? This was also the case with the energy-based models. So from energy-based models on, we always work with the continuous random variables usually, and then we think any discrete random variable that we have is just a quantization of that one, so that's going to make the life easier. Now, assume that this z is one continuous random variable coming from distribution Q, so this is a density function. And now I have one function f. This function takes one real number and transform it into another real number, right? So that is a real-to-real function. And then this function f is taking z and is going to give me x, right? Now, given that x is coming from a random process, I can say that x is also a random process, right? And the question that I have is that what is the distribution of this random process x, right? So I guess many of you had this problem as a kind of exercise in the basic probability courses. So exactly we're doing the same thing. Here I'm going to put a few conditions on f. I assume that f is invertible. It means that if I have like x equal f of z, then I can get back from x to z. Like there is one function f inverse, which is going to take x and give me back z, right? So it's a function which can go forward and backward, right? So it's invertible. The other thing that I assume right now for this particular example is that I assume that f is strictly increasing, meaning that when I increase z, the value of x is going to increase, right? It's always going up. And it's not hard to see that this means that the reverse function is also increasing, right? So if x goes up, if z goes up, x goes up, right? This means that when x goes up, z goes up as well, right? So the inverse function is increasing, the function itself is increasing. Life is very easy, right? Now, the question that I want to answer, I want to know what is the density of x. Any clue how we can find the density of x? How did you used to do it in the basic probability courses? You remember that? Okay, let's do it together. The idea is that we typically compute the cumulative distribution function, right? Because the cumulative distribution function is easily given in terms of the random variable itself, right? What is the CDF of x at one particular point A? Is the probability of x being less than a, right? This is the definition of CDF. Everybody's clear about that? Yeah? How can I compute PDF out of CDF? Derivative, right? So if you take the derivative with respect to the argument, then you're going to get to the PDF. So the classic approach for such problems in probability is that you work with the CDF because that is easy to compute, or at least easy to formulate. If you could end up with one expression for the CDF of x, then you're going to take the derivative, you're going to get the density of x, right? So let's do it together. So I'm looking for the probability of x being less than x. What is x? X coming out of the function f when z is going in, right? So x is f of z. This means that this is going to be the probability of f of z being less than or equal by a. Can I represent this interval in terms of z? F of z being less than a, what does it mean? So here is z, here is x, and this is our function which is increasing, right? Now, this is f of z, right? And now I want to know what is the chance. This is the point A, right? I want to know what is the chance of x being less than a. If I want to project it on axis z, what should I do? I should start from A, see what point I have here on the z-axis. What is this point? F inverse of A, right? So I told you that f is invertible, right? So it means that if A is f of z, then I can simply find z to be f inverse of A. Now, if x should be less than a, what should happen to z? Less than f inverse of a, right? So z should be on this side. Everybody's clear? Everybody's cool? Questions? So if you see it, the problem is solved. Everybody sees that? Yes? Great. So if you see that, then let's just replace it. So eventually, if I want to compute this guy, I can instead compute this one, the probability of z being smaller than or equal by f inverse of a. Now, can I compute that one? I know the distribution of z, right? What is that guy? That is indeed the CDF of z, right? This is CDF, the cumulative distribution of z, at the point f inverse of a. Everybody's cool? Questions? Okay, so if it's clear, now I want to get into the distribution, I mean the density function. How can I do it? I need eventually to take derivative of this function at the particular point A, right? So probability of density of x at point A, PA, is going to be derivative of the CDF function at the particular point A, right? Now, if I take the derivative with respect to A, what's going to happen? Can you tell me, looking at that expression here? Let's do it together. So I want to take the derivative of CDF of z at the point f inverse of a. Okay? Now, let me call this f inverse of a to be z. Okay? Or maybe I have z here. So instead of z, I put some other term, u. Okay? I want to compute the derivative of this guy with respect to a. Can you help me doing it using chain rule? What should I do if I want to use chain rule? Yes, how can I do it? Just tell me. D with respect to d, what is the first variable I should take the derivative? U, right? D to du, right? D to du, CDF of z at u times, what is the next term? Du to dA, right? This is the chain rule. Du to dA, right? Now, what is this guy? Derivative of CDF of z with respect to argument. There's a distribution of z, right? So it's going to be q. We showed it by q. So it's going to be q at point u, right? Everybody's cool? Everybody's following? Right? So if I want to do that, I want to compute this derivative. So I want to compute the derivative of CDF of z with at the point f inverse of a with respect to a. I am going to use the chain rule, right? So I'm going to take the derivative of CDF with respect to its argument times the derivative of the function inside the argument with respect to a. Everybody's clear? Questions of that? No question? Cool. So if you got no question, then this derivative, of course, this is the Q function, the distribution of Z. So I'm going to take Q and compute it at F inverse of A. And then I multiply it with the derivative of the inverse function, right? So that is going to be the solution to this problem. So the distribution of X is going to be distribution of Z computed at the inverse point times the derivative of the inverse function, right? And one other thing here is that the derivative of the inverse function can be readily written in terms of the derivative of the function itself. Anyone has any clue how I can do it? We're going to do it together, okay? Just take a look here. So I told you the function is invertible, right? Z is F inverse of X. It means that X is F of Z, right? Now, first of all, let's compute the tiny change in the both sides of the first equation. So Z is F inverse of X, right? If I want to see dx, a tiny change in x, how does it change z? So what's going to be dz? How can I write it down? D of z, the differential of z, is going to be derivative of the argument times dx, right? So I can write it down in this form. D of z is the derivative of this guy, which is the argument I have here, f inverse, times dx, right? What about this one? What can I do with this one? Exactly. So I can write derivative of f. So f dot here is f prime, like the derivative, the first order derivative of f. F dot times dz is going to be dx, right? Now, if you compare these two equations, can you tell me what is the derivative of f inverse? dz over dx, right? And comparing it to the second equation, can you tell me what is dz over dx? 1 over f dot. So the derivative of f inverse is 1 over derivative of f, right? At the point z. So you can conclude here that the derivative of f inverse, which is this first term here, is going to be dz over dx, which if you compute the same thing here, it is going to be 1 over derivative of f, right? And this is what we say the function inverse lemma, right? So you can even expand it to higher dimensions, actually. We're going to do it in the next slide. So, moral of the story, this derivative here, actually, you can also compute it in terms of the function derivative itself. So it's going to be 1 over f dot at point z. And given that z is actually f inverse of x, it's going to be 1 over derivative of f at the point f inverse of x. So this is going to give me much easier conclusion or solution to my original problem. So my original problem was to find the distribution of x, this px, and it's going to be eventually distribution of my z divided by derivative of my function. Okay? Now, one point that you can see here is that if I drop that assumption I told you initially, I told you that the function is strictly increasing, it's going up. But if it is even decreasing function, it's still okay. Everything going to change by a sign, and then that sign is going to cancel out. Okay? So I don't want really to do it again here, but if you are really interested, just redo this again at home, assuming that the function is decreasing, and you're going to see it's the same thing. Okay? Everything is going to be the same with only one sign change. So that is not really necessary to have increasing f, but it's really necessary to have our function invertible, right? Because we need to be able to compute f inverse at point x. If we cannot do this, we cannot compute this, any of this stuff we did here, right? So f function needs to be invertible, but it doesn't need to be necessarily increasing or decreasing. I mean, of course, you can understand that if your function is invertible in one-dimensional case, it should be either increasing or decreasing, right? But there is no necessity for it to be only increasing or decreasing. I mean that. So, moral of the story, you can have this formula, which is a quite well-known formula in probability, right? If you change a variable, so if you have z, and this is a random process, you pass it through one function f, then the output, which is x, you can compute its distribution using this formula. It's going to be the distribution of z itself, so it's going to be q at the point z, which is eventually f inverse of x, divided by the absolute value. So this absolute value is the sign change I told you. It doesn't matter whether it's increasing or decreasing. Always the sign going to figure out to be positive. Okay? So it's going to be absolute value of derivative of the function at the same point. Okay? So what can I say now? I can say that if I know the distribution of z, it means that I know q function, this red function. And if I do know my function f, I need to know the f itself because I want to compute the derivative of f. And I know the inverse of that function. So the function is invertible and can compute that inverse, right? Then I know the distribution of x as well, right? So what do I need? The distribution of the source, z, and the function, and its inverse, right? If I know these three things, I know the distribution of the output. Everybody's clear? Now, you can extend this idea to higher dimension. And the higher dimension is going to look like this one. So how does it look like? Well, here, as you can see, you're going to have the determinant in the denominator. I think I forgot the absolute value here. But I mean simply the absolute value, of course. So we're going to have the determinant here in the denominator. So instead of this guy. And then instead of the derivative, we're going to have the gradient, right? So we had the derivative of the function. Now we're going to have the gradient of the function because the function is multidimensional. But again, you're going to get the distribution of z. You divide it by the determinant of the gradient of f. And then you compute everything at the point z. And z is exactly f inverse of x. Everybody's clear? So if I want to know what is the density or the probability distribution at the particular point x, how can I compute it using this formula? I'm going to get x. I put it inside f inverse. I'm going to get z, right? I take that z. I put it inside q. I get one value. I also compute this Jacobian matrix, right? I'm going to explain it. No worries. I'm going to put it inside this matrix. This guy is a matrix. And then I compute the determinant and put it in the denominator. I'm going to get the density of x. Everybody's clear? Yes?
Sorry, Professor, you said something about missing like an absolute value?
Yeah, I think the whole thing should be like positive, right? Everybody's clear? Question? Yes?
Sorry, there's one question. Like, how do you get f in the first place?
How do I get what?
The function f.
Oh, f is some function that I have defined. This is going to be my model later. So this is what I'm trying to learn. Yeah? But yeah, f is something that I put it, right? So I assume that I have distribution of z. I put x and I want to know the output, right? Questions? No question? OK. So one point here first, this gradient of f that I write here is now a Jacobian. And you see it why? Because I assume that z is d-dimensional, x is d-dimensional, right? So it means that I have z1, z2 till zd, and then I have one function which is going to give me x1, x2 till xd, right? Now I can compute the derivative of x1 with respect to z1, x1 with respect to z1, x1 with respect to z2, x1 with respect to xd. It's going to be my first row, right? Then x2 with respect to z1, z2, zd, second row, right? And I keep on going till xd with respect to z1, z2 till zd is going to be dth row, right? So I'm going to have a d by d matrix as derivative. This is what we call a Jacobian matrix, right? This is a d by d matrix. Everybody's clear? Yes? OK. This is one thing. The other thing is that, again, like before, we need f to be invertible. I mean, I put it here differentiable, but typically the function f that we come up with is a differentiable function, a well-defined function. So that is not a crucial thing, but it needs to be differentiable so that that gradient exists, right? Those derivatives all exist. but it should be also invertible. The function itself should be invertible, because if it is not invertible, then this determinant is going to be 0, and then we cannot compute anything. You see here, in the denominator, you cannot have a 0, right? So again, your function needs to be invertible. And this is why I consider f to be d to d. It means that z space and x space, both of them have the same dimension. Because if z is of smaller dimension, then the function is not invertible anymore. If z is of higher dimension, this is not invertible anymore. Yeah? So you need z and x to be of the same dimension, and this is one of the bottlenecks we have when we look at the problem from this point of view, but this is a start point. Okay? So right now, z and x, both of them, are exactly of the same dimension. Clear? Because if it is not, then the function is not invertible. If the function is not invertible, then determinant of Jacobian is going to be 0, and then eventually we cannot compute the output density. It's impossible, right? So we need the function to be invertible, so we have non-zero determinant, and because of that, we're going to get this output density computed. Everybody's cool? Everybody's clear? So this is what we call it normalizing flow. People call it normalizing flow. And the idea is that when you have z, one random variable, and you flow it, you pass it through one function, you get a new distribution, and that distribution is essentially the previous distribution q divided, normalized by that term computed in terms of the derivative of your function, right? So the input distribution divided, normalized by the derivative of your function. This is what we call it normalizing flow, right? And normalizing is not coming from anywhere but the simple analytic discussion we had here, right? You really need that one to exist if you want to compute the density. Everybody's cool? Questions on that? No question? Okay, so if you got no question, then the idea of flow-based model is essentially the idea to somehow try to start from a very simple space, d-dimensional space, which you can actually sample very easily. For instance, you can think of it to be a d-dimensional Gaussian space. So you have one IID d-dimensional Gaussian noise. You sample z. Z for us is here the latent variable, the latent representation. You sample one easy z, and then you design some very complicated function f by a neural network, which somehow normalizes that distribution of z in a form that the output distribution is looking like your data distribution. You got the idea? So we want to start from the same arguments we had in the previous part when we talked about latent space. We want to have something easy to work with, and maybe we can start from some easy latent space. So we can start from a very simple distribution, and we assume that our latent distribution is that guy. So it means that I assume that z is original in this formulation. Z is one easy to sample distribution QZ, as I told you, some Gaussian noise, something very simple. And then I try to learn some deep model F here, so that I'm going to get my data sample out of it. Meaning that the output distribution, which I can compute using this normalizing flow formula, is going to look like the distribution of my data. Everybody's clear? You got the idea? So at the end of the day, we are going again to work computational, meaning that I'm going to put this model to be one deep neural network, and then I try to train this deep neural network so that, starting from a Gaussian noise, its output going to look like a data sample, right? And how can I make this happening? How can I train this deep model? Maximum likelihood. Great. So if you should learn one thing in this course, always maximum likelihood, right? So you're going to do maximum likelihood. You know the distribution of the output. That is going to be given in terms of your model, right? And then you try to train that model so that the likelihood is maximized. And this is going to somehow estimate your data distribution. So this is the whole idea in the flow-based models. I start from one easy QZ. I use this formula, which is going to normalize it to get the distribution of the output. Then I am going to play around with this value of W, right? And this value of W is showing up everywhere, right? It's showing up in this Jacobian. It's showing up inside Z as well, because Z is the inverse of this FW, right? So Z is depending on W, Jacobian depending on W. Now I try to play around with that W using maximum likelihood, such that this new distribution PW on X is going to look like my data distribution, right? Now, this is a very easier approach to generate a data sample then, right? Because once I have this function FW to generate a new sample, everything is easy. I just generate one noise, I pass it through the function, and then I'm going to get one data sample, right? And this is what most of the modern models are doing, right?